So this is chapter 9, Unsafe Rust. Unsafe Rust essentially enables programming features which the compiler cannot check the safety of. It fundamentally cannot check. So the unsafe keyword essentially means, trust me, I know what I'm doing. And this chapter goes into a lot of detail about some of the little nooks and crannies around that. This is a great diagram from the Rustnomicon, demonstrating the two faces of Rust. Lovely, safe Rust and bit spikier, unsafe Rust. In the Nomicon, it has this nice quote: unlike C, Rust is a safe programming language, but like C, Rust is an unsafe programming language. And I think those are the two faces of Rust. And there's this quote: so must become aware of properties that the type system assumes and audit them in any code that interacts with unsafe Rust. And I think it's that like awareness of the properties of the type system is like the crucial bit that when you're dealing with unsafe code, it's like suddenly you're satisfying these prerequisites that you maybe didn't even know existed. So with this chapter, kind of broke it down into what is unsafe Rust, why we need it, and the tooling that's available to make unsafe Rust safer. So what is unsafe Rust? This is going to be, hopefully familiar to a lot of folks, the initial part at least, but hopefully there'll still be some new bits in it, but I think it's important to recap some of the kind of fundamentals. The unsafe keyword has two uses: declares the existence of contracts and declares that the programmer has checked those contracts. So we'll go into detail about what those contracts are, but the unsafe keyword means the compiler can't check something and we need the developer to check it. You'll see the unsafe keyword in 4 places. So in unsafe blocks, unsafe functions, unsafe traits, and then the unsafe trait implementations. With an unsafe block, that allows you to, inside your unsafe block curly braces, do the operations that the compiler can't check the safety of. But all your other normal like safety guarantees that we know and love about Rust will still apply. So you still won't be able to create, have access to mutable references if they're just normal vanilla references. All your normal rules still kick in. But in an unsafe block, you can also do things like dereference a raw pointer, call an unsafe function or method, access or modify mutable static variables. So that's like a global, or implement an unsafe trait or access fields of a union. That's like a C style union where, you won't necessarily know what the type is that you've actually got. So you could essentially be doing a weird cast there. Taking this example of get unchecked, which is an unsafe method that you can call, by putting it in an unsafe block, you are saying, as the caller, I am doing the bounds check. I know that this is within range. You don't have to do any checks within the get unchecked method itself. And because it's an unsafe function, it requires you to use an unsafe block. So this here is unsafe, telling you this function is unsafe, which means there's some constraint that this function has. And if you call it, you need to make sure that you have satisfied those constraints. So going back to the get unchecked example, you're saying that the index that you've used is within range. And you normally, whenever you create an unsafe block or call an unsafe function, add a comment in there to say what those conditions were and how you've satisfied them. So in this case, I've just said, I was very, very careful. Don't put a comment like that. Put a comment that actually describes what the constraints were and why you can say with certainty that they're satisfied. When you look at unsafe functions, the doc tends to be pretty long deliberately because it has to accurately describe those safety constraints that the caller has to satisfy. So in the case of get unchecked, it says safety. Calling this method with an out-of-bound index is undefined behavior, even if the resulting reference is not used. So that means as the caller, you have to make sure that the index is not out of bounds. If it is out of bounds, all bets are off. And we'll talk a bit more about undefined behavior later. But yeah, that's what essentially all of the things you're doing around unsafe Rust are to avoid. You want to avoid undefined behavior. There is no scenario in which you want undefined behavior. If we dig down one level into the get unchecked method that's called from this method, so this is the get unchecked function itself. Within it, it's also calling get unchecked, but a different version of get unchecked. And in this case, it has the same safety comment, but this time it's saying the caller of this function has this safety requirement. Therefore, this call inside the method must satisfy those safety requirements. So it's kind of forwarding on the safety from the caller. Like if the caller satisfied the conditions, then I've satisfied the conditions. And then within that method itself, you might have like an assert here that wouldn't fire in a release build to check whether you've actually satisfied those conditions. But in a release build, this is all you would get. You would just be doing another unsafe block, but not doing a check again on the bounds. And again, forwarded on the safety to say, look, the caller's guaranteed this, which means it has to be valid to do this check here. There's also, this kind of intrinsics assume, which is, oh, okay, apparently my mic's getting quiet occasionally. I'll try and hold the cable. Hopefully that'll help. Where you see this create intrinsics assume, what that's doing is saying any code can assume that this index is less than the length of the slice. And that's anywhere in the code, not just within this block. That's saying anywhere the compiler can assume that. The LLVM assume allows the optimizer to assume that the provided condition is true. The information can then be used in simplifying other parts of the code. So this is where undefined behavior can really creep in, is because the compiler is trying to optimize the hell out of everything. And if there's little assumptions that it can make, if those assumptions get broken, then other bits of the code can break that were totally kind of unrelated, that you wouldn't think would be affected. But that's why it's kind of this undefined behavior means weird things can happen. And then this is the actual inner check. So this is what's actually doing the get unchecked here. No undefined behavior check. So now we're calling down into an actual intrinsics method. And again, the caller's already checked the preconditions. We've just forwarded it all the way down. But fundamentally, it was us at the very calling point that had to satisfy those conditions. When you create your own unsafe function, it currently implicitly contains an unsafe block, which means you don't have to put the additional unsafe brackets in here that it had added. Because this function was unsafe, you could have gone without those. But, do you want to do that? And that's one of the things that Jon calls out in the book, as you probably should put brackets in there, because you could have potentially like fairly long function. Not all of that will have necessarily the same like unsafe constraints as the calling function. By having an implicit unsafe block, you are saying that those constraints that the calling function had are the same as the constraints of any unsafe call inside it, which isn't necessarily true. And it can get like confusing then to say, okay, who is actually verifying this unsafe block? Is it me, or is it the calling code? So it's generally considered best practice to have explicit unsafe blocks in unsafe functions. And we can turn on a limp for this. So you can add this into your code, and that will mean that it will warn you if you try and do an unsafe operation in an unsafe function without an additional unsafe block. And actually from edition 2024, which is coming out later this year, it's going to warn us by default, which will be great. So you can have a look at the pull request of that and see it in the guide. But if you turn on the warning now, if you're writing unsafe functions, then you'll get that warning, and you can fix all those cases ahead of the 2024 edition. They will have a fix option, obviously, when you upgrade to the next edition anyway. If you turn on that warning, then you end up with something like this. Says, this is an unsafe method and it requires an unsafe block. This is inside an unsafe function, but the body of that function should be safe by default. So that's what that warning lint will give you. And we can then fix that by adding in our unsafe brackets. And we should add some kind of safety comment that justifies why our unsafe call is reasonable. The next place that you might see unsafe is unsafe traits and trait implementations. They are, unsafe traits are just traits that are unsafe to implement. So again, there's some kind of constraint that the compiler can't enforce, but you can justify as someone writing the code as a programmer. And they're safe to use, so you can rely on those traits. Once those traits have been implemented, they're fine. It's just the implementation that's considered unsafe. And sync and send are the classic examples. They're auto-implemented if all of the contained types within your type are sync and send. But if there's some type in there that isn't sync or send, then your parent object won't be. And again, declares the existence of contracts that the compiler can't check. What those contracts are is in the documentation for sync and send. So we've talked about this at various other kind of sessions before, but a type is send if it's safe to send to another thread, and a type is sync if it's safe to share between threads. So a T is sync if and only if ref T is send. So if you can send a reference, which essentially means you're sharing it between the threads, then it must be sync. If you incorrectly implement send or sync, then you can get undefined behavior, which we obviously don't want. But there are cases where you do need to implement send and sync. So you want to know, how do I ensure that I'm upholding the safety guarantees? Those of you who came along to the previous book club, Rust, Atomics, and Locks, you'll already be familiar with implementing these traits. In terms of types that aren't sync or send, raw pointers is the classic example, but also unsafe cell isn't sync, which means any type that contains an unsafe cell, for example, cell and ref cell, are also not sync. RC isn't send or sync, and that's because the ref count that it relies on isn't atomic. That's why you use arc if you're dealing with multi-threaded code. So in the case of sync and send in the Atomics and Locks book, in chapter 4, we created just a naive spin lock. And in that case, we created a safe API onto our type, which ensured that the unsafe cell could only be used in a thread-safe way. We were never going to have multiple mutable references to the data inside it because we were locking it with our atomic bool using a lock guard API that would always be valid, and you could only ever have one mutable reference to the data. So that means we know that it's safe to implement sync for this spin lock, provided the T inside it is send. And that kind of restriction on saying that the T has to be send is very, very important, and that's something that you don't want to don't want to miss. Another example of an unsafe trait is the global alloc, which is one that Jon mentions in the book. There's these required methods, alloc and dealloc, and then there's some provided methods. But there is a safety contract as well, and that safety contract says that it must not unwind, the global alloc must not unwind, and layout queries and calculations must be correct. It's interesting that it says in general must be correct. I was like, okay. And it must not rely on allocations actually happening, even if there are explicit heap allocations in the source. And that's kind of like a subtle thing in that you wouldn't know if you didn't read the doc for the trait. And that's why, again, there's this contract that has to be upheld by the allocator. So it's this idea, if the code explicitly calls an allocator API in your code, you cannot assume that the allocator has actually been called, because the compiler can do what it wants. And so your allocator cannot rely on allocations definitely happening, which is kind of interesting. And those are the kind of contracts that you see with these kind of traits. So why do we need unsafe? We need it for things like interfacing with other languages. Foreign function interface is going to be chapter 11, which Tim's kindly agreed to take, so we'll hear more about that then. We're going to need unsafe if we want to interface with hardware. There are also certain performance considerations. There's certain cases where the compiler can't make an optimization that we want. And if that's the case, then you might have a small unsafe block in order to create that optimization. There are also some minor borrow checker limitations, and these might go away in the future. Like hopefully the number of places we need unsafe over time will reduce because the compiler will get smarter at figuring things out and being able to optimize things for us. But until then, until the borrow checker is smart enough to do certain things, you will have unsafe. And as already mentioned, we need unsafe to flag up some custom invariant to the caller. So if there's something like the global allocator that needs to have specific behavior, we don't want to just like freely kind of expose that. We want the caller, we want the person who's using our function or using our trait to know these subtleties. And by requiring them to have an unsafe keyword, it's kind of like a, whoa, hold on, take a second, read the docs here. This is not your everyday code. The main use of unsafe Rust is when working with raw pointers. So they're special because they can ignore the reference borrowing rules. That doesn't mean you should, but they can. So that means you could have both immutable and mutable pointers or multiple mutable pointers to the same location. You shouldn't. You should never have that. But if you're working with raw pointers, you could. So if you've got Unsafe Rust, you're saying, I will make sure this isn't the case, even though raw pointers have no way to ensure that. They also aren't guaranteed to point to valid memory. You could create a raw pointer that points at basically anything, and then you've essentially created garbage. And they're allowed to be null. And, anyone, especially coming from the C and C++ world, will know null pointers, yeah, they're not the worst thing in the world, but they're not great either. And raw pointers don't implement automatic cleanup, so any of the data that they're actually pointing at needs to be handled in some other way, or you need to be actually managing that memory yourself. You can use the raw pointers then to call out to external code. So in this case, we've got the foreign function here, and we're using the extern keyword to then call out to it. Now, in this case, we're doing unsafe because we're just calling out to that function. The function isn't doing anything unsafe. We know there's nothing dangerous about this, but the compiler doesn't know that. All the compiler knows is that we're calling out to some function, and then we're coming back, and who knows what could happen on the way. So, if we were going to add an unsafe comment here, it might be like description of what this function actually does and why that's safe. We're saying that there's no preconditions on this. Anyone can call it. There's no issues. Just to briefly kind of segue in, like, foreign function interfaces, we absolutely need these. You can't just rewrite everything in Rust. And one of the examples is like, the Python interpreter Pyo3, like you need to be able to interface with other languages to create these like amazing tools like Pyo3. There's also unsafe functions that, again, just couldn't exist in Safe Rust. So for example, read unaligned. If you're using read unaligned, then the caller has to ensure that the source is valid for reads and points to a properly initialized value of t. And interestingly, there was a recent CVE now bumped up that was talking about using representation packed of structs, the order of that not being guaranteed. And if someone's using read unaligned, but they're expecting things to be in a certain order in a struct, that actually isn't the case for repapack. You need to have repa c comma packed, and the compiler might take advantage of that, and indeed it's probably going to at 1.80. So yeah, so that's another interesting example. There's also spawn unchecked, which means you can use reference data that isn't static, and you might need to do that for some reason because you know that that data is not going to live long enough. And I imagine this probably existed before scope threads existed as well. Yeah, but it's another example where you're saying, look, I'm going to ensure that any references that I'm using within this thread are going to be alive for the duration of the thread. I'm going to make sure that I join on the thread before these references go out of scope. What could possibly go wrong? This seems, so far, all you have to do is uphold some guarantees and you're golden. Well, the compiler has quite a few guarantees that it makes. It's guarantees that you're not going to have any out-of-bounds access in Safe Rust. Mutable references to data are exclusive. We're not going to have any data races, and we're not going to read uninitialized memory. And that's not the only set of guarantees that we have, but those are like the main ones. And any unsafe Rust could violate these. So we have to be really, really wary of these, but there are other guarantees as well. And going back to like raw pointers, with unsafe Rust, I mean, actually with safe Rust, you can cast between an immutable and mutable reference to its corresponding raw pointer type. So that's the other kind of thing about unsafe is it doesn't mean you just have to read the code within the unsafe block carefully. You have to read the surrounding code. You use the safety kind of comment around your unsafe block to say why those invariants, why those constraints are satisfied. But that doesn't necessarily mean that the code showing that is in the unsafe block. It might be higher up. So in this case, this is essentially creating two, you've got a mutable and an immutable reference to the same data, which we absolutely shouldn't have, but we do. And even though within this block, there's nothing unsafe happening, here is where the actual kind of problem is. But if we were saying this, we're saying, look, if I'm dereferencing a pointer, I have checked that that pointer is reasonable to dereference, which means I know that if it's mutable, that it's a it's an exclusive access, And in this case, that isn't being upheld. You would have to look at the code above to call it out. So it's this, the dereference is unsafe, but that doesn't mean that the dereference is where the damage has been done. The damage might have been done in safe code. You can also do things like create an invalid pointer and then just make it go boom. So you can create a pointer. So here I'm doing something that makes no sense to do, and then I just dereference it and get a segfault. And again, the unsafe block is where it's doing the dereference, because this is where the undefined behavior is actually happening, but that doesn't mean that's where the logic problem is. The logic problem might be outside of the unsafe block, but it's causing your constraint to fail. Basically, you have invalidated your Rust code by writing something that doesn't make sense. And similarly, dereferencing a null pointer, undefined behavior. I did want to go on like a brief segue talking about dereferencing null pointers, because I just happened to notice that in Compiler Explorer with optimizations off, in the assembly, you can see that it's going to panic even kind of before you run it. So yeah, but in release builds, it makes it through. And so I did a lot of Googling around, and most operating systems map the null pointer's address such that accessing it causes a segmentation fault, and it's not going to cause something else weird to happen. But actually, that's not guaranteed. Something else could happen. You could get something else weird other than just a segmentation fault. You could get something else even weirder if your target system so desired. And obviously, that's not even considering the fact that the compiler is allowed to assume things before that. So when you're dealing with like undefined behavior and unsafe code, it's good to clarify the difference between unsound functions and undefined behavior. So if a program violates the rules that the compiler is allowed to assume are being upheld, then the resulting execution will have undefined behavior because you have violated one of those rules. The optimizer has assumed those rules have all been upheld. Things can get shuffled around. Your code can do strange things because you didn't uphold the contract. But if a library provides a function which could lead to undefined behavior, then we call that unsound. So unsound means it could produce undefined behavior. There's a really great talk, Unsafe Rust and Miri, by Ralph Young, which kind of really spells out the difference between undefined behavior and unsound. I want to add like an additional unsound definition, which is that if your library provides an unsafe function which can lead to undefined behavior in code which satisfies all the documented safety requirements, then it is also unsound. Now, I don't know if that said, I wouldn't say that that's not an official definition of unsound, but I think that's also important. Is unsafe functions are kind of weird, where it's like the doc for that function is all you get in terms of finding out what conditions you as a caller are supposed to uphold. Because you don't know what that function's doing with your data. You're kind of trusting it to say, look, these are what you have to uphold as your conditions. And if you uphold your side of the bargain, I will promise not to produce undefined behavior. But if you as the caller uphold your side of the bargain and they still produce undefined behavior, then it's unsound. Maybe because there's some other constraint that they didn't document, or it might be, it might be a safe API, in which case, yes, definitely unsound. In the Nomicon and also in the Rust reference, you can see what guarantees Rust really requires that you uphold in your code, whether it be safe or unsafe. But the only one where you as a developer have to uphold it is in the unsafe code. So Rust code must not dereference dangling or unaligned pointers. It can't break the pointer aliasing rules. So that was the thing we talked about quite a few times, about the fact that if you have a mutable reference to some data, then it needs to be exclusive. No one else can have a mutable reference, and no one else can have an immutable if you've got a mutable one. Rust code mustn't call a function with the wrong ABI or unwind from a function with the wrong unwind ABI. It mustn't cause a data race. It mustn't execute code compiled with target features that the current thread of execution does not support. What does that mean exactly? And it mustn't produce invalid values. What constitutes an invalid value is quite a fairly long list. So a bool that isn't a 0 or a 1, an enum with an invalid discriminant, a null function pointer, a char outside of those ranges, a never return type, an integer floating point value or raw pointer read from uninitialized memory or uninitialized memory in a string slice, a reference that's dangling, unaligned or points to an invalid value, a wide reference box or raw pointer that points to invalid memory, lots of, invalid metadata. So the invalid metadata is a slightly interesting case. So in the case of a dynamic trait metadata, it might not be pointed to the correct type of V table that you expect, or a slice metadata where the length is not a valid usize. And it also can't be a type with a custom invalid value that is one of those values. So if you have a non-null type, that can't be null. That's in your types definition. And if it is null, that's undefined behavior. And this list is not exhaustive, and they take pains to like emphasize this. Rust is trying its best to define all of the things that constitute undefined behavior, but that list can change over time as new things are figured out as being like, okay, no, actually, you can't allow this, or this is too restrictive. We could maybe actually make this a little bit more flexible and allow this in certain cases. But generally, this, if you're doing normal stuff, you don't have to worry about this. But if you're doing weird stuff, you need to be really careful about what the compiler is allowed to assume and making sure that your code does not violate those assumptions. Like you can't just take advantage and be like, oh, I'll use this null type, but I'll just make it null anyway and just use that. And I'll do some other kind of like clever bit things to make that work. It's like, no, if you've done that, you've got undefined behavior because the compiler is allowed to assume that it is never that value. When you're writing unsafe code, one of the things you have to be careful of that Jon points out is panics. Because bad safe code and good safe code, sometimes you want to panic, can panic. So if it panics, that panic can unwind the stack. And any unsafe code we write needs to be able to handle that. And again, the Nomicon does a good job of talking about exception safety. If you're writing your own unsafe code, read the Nomicon very carefully. But here's the example from the Nomicon. It's slightly different to the example in the Rust book. They're both very similar and very good, but I thought I'd use this one. This is an example of what a push all function could look like. This is not what the push all function actually looks like. The idea is here, I'm reserving the memory I'm going to need up front so that I can just write the data. And that makes sense. It doesn't matter that this is ending up with, uninitialized data in there because we're gonna write to every value in there. And it can't overflow because we just reserved this. So we just reserved it, and now we don't have to do checks on every index. We can just go in and write the data. But this panics if this panics, which it could, then our uninitialized memory could be read, and that's very bad. So when you're writing a function, you need to think, is there anything here that's outside of my control, or is there anything here that could panic? And in this case, it's the clone. The clone, we don't know what this type T is. We don't know if their clone has some kind of panic condition or not. But if it can panic, then we're in trouble. So to fix this, we can just set the length every loop iteration, just increment it, and still can't overflow because we've reserved it with the length up here. And so even though the clone is out of control, we know that the length is going to be fine. And actually, is it going to be fine? Maybe not, but in any case, you wouldn't do this way anyway. But it's still that same idea of if you're doing something that could panic, you need to make sure that your code can unwind safely without leaving uninitialized memory that's going to attempt to be freed as if it's the type T when it isn't the type T yet. Yeah, exactly. You need to move the set length to a line below in this one. So ignore this. That needs to be down here because if the clone failed, then you haven't written the memory yet. Of course, is that still definitely fine? I guess it depends on what the clone does. No, it should be fine. It should be fine. Okay, so then there's another example of an unsafe function from raw parts. This is one which creates a slice from a pointer and a length, and the length is the number of elements. So in this case, we're creating a slice here, and there's a bunch of conditions in the doc again. So that's the classic thing with unsafe code. It should have very clear doc. The data has to be valid for that many bytes and be properly aligned. And the entire memory range for this slice must be contained within the single allocated object. And slices can never span across multiple objects. Data must be null. So there's a whole host of like conditions here. Condition 2 was the data must point to a length consecutively properly initialized values of t, and the memory reference in the return slice must not be mutated during the lifetime to A except in an unsafe cell. And the total size of the slice must be no larger than I size max. But you can, if you misuse this, it might not be like immediately obvious how you're misusing it. So if you say you wanted to write a safe API that takes 2 slices and then joins them together, and this is the example that they give in the doc for this function. You write this function, you say, okay, well, I just need to check that these 2 slices definitely can be joined together. So I'll just check if they are contiguous. So I check that they're contiguous. If they are, then I go ahead and use from raw parts to connect them. But actually, there's still a hole in this logic. Checking that they're contiguous is not enough to ensure that those slices are definitely from the same object. So here, A and B are totally different allocated objects. And then when I try and join them together, I've got undefined behavior. There is nothing unsafe in this function call. So there's nothing wrong. This code is correct. What's not correct is this join slices method is unsound. There is a way you can call it with safe code that results in undefined behavior. Therefore, that function is unsound. So there's a lot of ways you can cause issues with Safe Rust. With Unsafe Rust. So how widespread is Unsafe Rust? How much do we need to worry about it? I'd say like as individuals, we don't need to worry about it very much, but there's this really nice post from the Rust Foundation. They did like a study of the crates and they found that nearly 20% of all crates have at least one instance of the unsafe keyword, which is a lot. There's a lot of crates that use unsafe. And it's not clear from like the post whether or not this was including like macro expansions that it's pulled in from libraries and yeah, but it's it's a lot, and you're hoping that all of those cases are fairly simple and straightforward and that the soundness of them is solid, but how do you ensure that? So we can't just like ignore unsafe. It is very important for all the reasons we've said, but even beyond that, people seem to use it more than you would think. I just wanted to do like an honorable mention as well to undefined behavior in Safe Rust. So we talked in chapter 1, maybe, about covariance and contravariance. And that was also like around the same time that if you've heard of the crate CVERS, which is a crate which basically abuses the contravariance rules of Rust to create undefined behavior in completely safe Rust. So this is what that code could look like. This is one way you could do it. I'm not. How much do I explain it now? Do I have time? I'll try and explain it a little bit, but you basically, in the case of parameters, so if I have a parameter that takes a reference with a lifetime A, I can always pass a parameter that has a longer lifetime, for example, a static lifetime to it. And that is necessary in order for you to be able to use, pass a string slice that's static data to a method that can also take a string slice that is data that's on the stack or on the heap, or any string slice that's somewhere else that's not a piece of static data. So that's necessary. And then on the return type, similarly, you just need the reference that's returned to live long enough. You can always return a static reference from a function that you can use if the return type is static, then you can use that in other places. And if your restriction on the return type is just that it has to live of like a lifetime A, then you should still be able to return a thing of lifetime static. You just have to return something that lives as long as it's going to be needed. So you can basically abuse that by doing something like this, where you essentially have passed in this thing with a lifetime of A, and then you end up returning something out that has a lifetime that's longer. You've extended the lifetime. I'm not going to explain this in great detail, but if you can watch chapter 1, or there's a video on CVRS that I think does a decent job explaining it. But essentially, this is completely safe Rust, and with it, you can implement all kinds of undefined behavior with not even a single instance of the unsafe keyword. In reality, you are never going to accidentally write this, so it's not an issue, and it's also probably quite easy to spot as like malicious code because it looks so strange. But yeah, it still could be done in theory, and they might close this like loophole maybe somehow, but they've known about it for a long time. But yeah, the end result is you essentially end up with garbage. So in this value here, I've just got nonsense. I started off with 1, 2, 3, and then I've ended up with 0, 0, 1, 4, 8, 7, 7, 9, 8, 2, 8, 8. Like that's not what we wanted. Oops. Sorry. Sorry. There we go. So that's our undefined behavior in Safe Rust. That was just like a brief segue, but it is slightly related to what we'll be talking about shortly, which is making unsafe Rust code safer. One of the tools that's available to us is Miri, which is a mid-level intermediate representation interpreter. So Rust goes through an intermediate representation, and Miri is an interpreter for that intermediate representation. And it's now not only used for helping make your unsafe code safer, but it's also used within the compiler for doing const expr stuff. But it can look out for undefined behavior such as out of bounds memory access, use after free, invalid use of uninitialized data, and more. And it can even look for memory leaks, which are not undefined behavior. They are completely reasonable in Rust, but Miri can look for it. It can look for objects that are still allocated at the end of your program. And it's super easy to use. So if we take the earlier example of dereferencing a null pointer, all we have to do is, have installed Miri, which you can do very easily by just adding component Miri, and then you run your code, or you run your test code with the nightly flag and Miri. So you do cargo plus nightly Miri run, or cargo plus nightly Miri test, and then you get an error like this, which is super clear. Memory access failed, null pointer is a dangling pointer. So this memory access failed, indicates a bug in the program, tells you where it is. Incredibly useful. And it works for, this is obviously a very, very simple case, but it does work for more complicated cases as well. For example, that non-unsafe unsound code that we were looking at earlier, it will catch that. Now, it's not as easy to read, but it's still, it's still not bad. Basically saying this print statement at the end where we finally actually access this data was invalid. So construction invalid encountered a dangling reference, use after free. So we know that somewhere in our code there's a use after free. It doesn't necessarily point us at exactly where it is, exactly where the problem is, but it still, it still tells us that there's a problem. It still identifies the problem. So that's pretty nice. But it only detects issues with executed code. So it's really important that your test suites in your unsafe library cover all the kind of cases that you want to cover, because it will only detect issues with executed code. And it won't detect everything. It's not perfect. And it doesn't work over the vast, vast majority of foreign function interfaces. So there's like a few specific things it can do, such as like reading files it can handle, but it can't handle most FFI, which means if you're doing any kind of wrapping of anything, then you're stuck. Miri won't help you. But it's still pretty good. Also want to call out cargo careful. which again makes use of nightly, but unlike Miri, so it's a bit simpler, it doesn't catch as much, but it opts into nightly only checks that help detect undefined behavior. And it also uses standard libraries, so it uses a version of standard library with debug assertions to catch things like alignment issues such as this. And it's owned by Ralph Jung again, who's the person who also works on Miri and did that talk that I mentioned earlier. I'll drop the links in Discord after this to all those things. So why would you use this? You'd use it because it works on all code. So like I mentioned, how Miri just will refuse to, well, maybe didn't make this clear, but Miri won't compile if you're doing FFI functions it doesn't recognize. Whereas cargo careful will still it'll still run because all it's doing is enabling the checks that are in the compiler and the standard library that it doesn't normally have turned on. So even though it won't be able to check your FFI code, it won't help you catch undefined behavior with your FFI code. It will still help you with other bits and pieces, whilst without you, it won't just refuse to run at all. And it's faster, it's much lighter weight, it's much smaller. It won't catch everything, but it's a nice kind of like midway point of like catching some things. There's also at your disposal sanitizers. So again, if you're coming from a C++ background, you might be well familiar with a lot of these. But these sanitizers can be used to detect out of bounds, access to the heap, detect use after freeze, use after return, memory leaks, etc. There's also control flow integrity sanitizers. So these are like the different sanitizers that you can use from Rust very easily. There's a hardware-assisted Rust sanitizer, kernel control flow integrity, leak sanitizer, memory sanitizer, and thread sanitizer. So if you want to use any of these, it is also super, super easy. Again, you need nightly, and then you just do sanitizer equals either address, CFI, HW address, KCFI, leak, memory, or thread. And then that's all you have to do to run these sanitizers, which I hadn't appreciated until I did this talk, how easy it is to run the sanitizers on your code. So you add export Rust flags, and this is all in the Rust dev guide, and then you can run with those sanitizers. And you can end up with an error like this. So this is the output that I got with the safe undefined behavior code. So this is stack use after scope on this address. And it even tells you the memory access that you were trying to access was actually inside this variable, which is on line 46. Borrowed data, line 44. So it gives you like clues that you could then use to try and figure out what actually went wrong. But the important thing is, there is some kind of undefined behavior going on, which means there's a bug in your code that you need to fix. So, in kind of wrapping up conclusions, Unsafe is a really useful tool. You need it for performance optimizations, you need it for FFI, you need it for a bunch of things. But all unsafe code should be approached with caution. And yeah, I'd recommend watching that talk by Ralph Jung, because he gives some really nice examples of undefined behavior and just how it doesn't, it's undefined because it doesn't behave how you expect. So it gives an example of like reading uninitialized memory, putting it into an int, and then having a method that says, okay, is this less than this value, equal to this value, or greater than this value? Is it any of those? So it should always be true, right? It should always be either less than, equal to, or greater than. But that returns false because it was the variable that was passed in had undefined behavior. But if you change the condition to be greater than or equal to, it miraculously starts returning true. And you can't really like reason easily about undefined behavior because there's so many things that could happen. So you really don't want to, if you start trying to reason about like, oh, well, maybe I can take advantage of this. No, don't. It's undefined because it can change in the future. Optimizers can change. You could have something that works in one Rust release and then breaks in the next for just arbitrary reasons. So you really want to make sure you don't have any undefined behavior in your unsafe code. And those unsafe boundaries should be managed carefully. So turning on that warning flag is like one step to help you. Like you shouldn't be doing unsafe calls inside your unsafe functions without an additional unsafe block, because you really want to separate like which of these constraints are the caller's responsibility and which of them are my responsibility as the unsafe function author. am I ensuring this, or is it relying on the conditions that I have asked the caller to uphold? So you want to manage those boundaries carefully. And documentation is essential. That is the only tool you really have as an author of unsafe functions to tell your caller what they need to do in order to make this not produce undefined behavior. But there is tooling to help us, like Miri, like Address Sanitizer, and those rely on you still having good test coverage, so they don't replace you just needing to reason around your code, but they're really useful for catching issues in real production code, including the compiler. There's a lot of resources on this. So I haven't covered everything that's in this chapter. There's a bunch of stuff that I'd recommend. If you haven't read the chapter, I'd recommend giving it a read. I thought the drop check section was really interesting, but I just didn't think I would have time to cover it, so skipped it. But yeah, Jon Gjengset, the author of the book, also did a talk at Rust New York City, which you can watch. The Rustnomicon is a really great resource, and also very well written and very easy to read, I would say. The Rust book has a section on Unsafe Rust, and we did a previous meetup on the topic. Miri's blog, this is from Ralph June again, who was one of the people who I recommended the YouTube video of. It's also this blog series by Chris Latner, who is the author of LLVM, what every C programmer should know about undefined behavior. It's like a 3-part series just talking about because all this undefined behavior is, it's a lot of the best resources on it are coming from C and C++, and Rust, as everyone knows, uses LLVM, and a lot of the undefined behavior that it's describing, and the sanitizers are all, at the LLVM level. So yeah, I would recommend that series, and then that series links out to this series of blog posts, which is a guide to undefined behavior in C and C++, which is also in 3 parts, which is also very good. Yeah, and then Unsafe in Rust, Abstraction Safety, Contract, and Public Escape is another blog that's linked. Recommend. Unsafe Abstractions. Anyway, there's a bunch. I'll drop these in the chat, but there's a lot of resources on it. You generally you don't really want to be writing Unsafe Rust for no reason. So make sure you do have a good reason when you're writing it. But it's also nothing to be afraid of. It's just you need to understand what you're being asked of the compiler. The unsafe keyword it means that you are taking on responsibility for the safety, so you should take it to heart. And yeah, that's the end of my presentation. We've got 5 minutes for kind of chat questions. Yeah, let me know what you thought of the chapter. There's a lot to cover, so hopefully it made sense, and I didn't even cover everything that's in the chapter. So if anyone wants to mention anything that they took away from the chapter that I haven't mentioned, then please go ahead.
Thanks, Ciara. That's great. I'm getting mocked on the chat for saying I use Unsafe for performance. The cowboy emoticon. So rude. No, I found that when I was writing an emulator where I was emulating the memory, which is a big array, I found that the bounce checking was just killing the performance. So I decided to just use a pointer to a buffer and index a pointer to get past the bounce checking, because I knew the size of the array was 64K, and I was using a U16 to index it, so I knew that it could never be out of bounds. And so using unsafe to inside a sort of memory struct and memory implementations block to get around those things. So call me a cowboy if you want to. I don't care.
No, exactly. You shouldn't not use unsafe because you have to enforce constraints. It just means, exactly like you were saying, you need to uphold those constraints. So if you're using it just as you were, then you have to know that it's going to be fine, and make sure that your code won't accidentally get refactored such that it's not a U16 anymore and it breaks in the future, kind of thing.
I probably am a bit of a cowboy with my code, though, to be fair.
I think cowboy is a compliment. It's very cool, huh? And when you see this is a hot pass, why not?
Let's put unsafe in every line. If we write it like C++.
it would still be better because you'd still have all of your safety guarantees. So yeah, and actually you made a good point, Tim, which is just if you're if you're using unsafe for optimizations, you do want to make sure that it's that is actually where your time is going. If you've got a application you're trying to speed up, is the bit that's you're thinking you should change to unsafe actually where the time's going? Because sometimes it really will be, and just changing to unsafe and skipping the bounds check can make a huge difference, but not always. So you want to make sure it's in the right place.
Oh my God. So in the chat, someone mentioned, I can never read that name. If you do rust up doc -- nomicon, it'll bring up the nomicon, Rust and nomicon web page, which is brilliant. Didn't know that.
Nice. Yeah, that's Oil and Shekel, aka another Tim. Tims and Mats, we seem to be collecting them. I like it.
Tim is almost Matt backwards. Almost.
Mit.
Like in German, mit means with. You know that?
Matt, Mitch, Tim. But yeah, how did folks find the chapter in general?
So
I thought it was very unsafe to read, so I didn't.
I rushed through it before the meeting, like just 1 hour before it, and it was very good. Now, like in your presentations, there were so many examples, so that was very helpful. But let's say coming from C++, like we know a lot about unsafe and undefined behavior. Also, we don't understand at the beginning what it is. Like when I started C++, I wasn't ever thinking so much about undefined behavior like nowadays.
I don't think I ever want to look inside the code for the CVERS crate. I think my head would just explode.
It's not too bad.
The code you look at that, I had no idea what you were on about.
Because I didn't explain it. I was like, can I do this off the cuff? And then I was like, as soon as I started trying to explain it off the cuff, I was like, oh.
I look at the code as well. I was like, I don't see a problem. What's going on here?
Yeah, chapter 1 in Rust for Rustaceans on the section on covariance and contravariance, combined with the video on CVRS, I think explain it in combination pretty well. But it's just the idea that like you can substitute like subtypes for their parent types, right? But in the case of return types, it can work the other way around on functions, and then you basically take advantage of that by saying this function is a subset of this function, and then essentially extend the lifetime, because the compiler doesn't know that that's a problem. That is, again, a terrible explanation. There's a YouTube video that explains it fairly well, but it does kind of rely on you already understanding what covariance and contravariance is. So I'd say, yeah.
I think you're just trying to explode my head.
We'll do a talk on it at some point, like maybe, but actually I'll actually prepare for it, so that I find it very hard to describe verbally, because I'm worried I'm going to mess it up. Yeah, I think one thing that I take away from this chapter is like when I was like, it's very like information dense, and I got a lot of value like looking for other resources as well, and I found there's a lot of really good resources on Unsafe Rust. I don't know what I was expecting, but yeah, there were even more than I thought there were going to be. And in terms of undefined behavior, I didn't really get a chance in this talk to like demonstrate the examples of like the weirdness that undefined behavior can cause, but I would recommend like, yeah, this series of like talk about undefined behavior in C and C++, because it's the same thing. It's fundamentally the same thing, and it's not just behavior that you don't know. It's like it's undefined because it isn't defined. It can change. The compiler can optimize stuff and do things based on those assumptions that can really mess you up. So yeah, and like in C and C++, for example, you don't have the issue of, so when you pass two references to a function, in C and C++, you don't know if those are references to the same data, which means you can't take advantage of the fact that they're different. Like you can't assume they're different. You have to assume that they could be aliases for each other. Whereas in Rust, you know that if one of them is mutable, that it's an exclusive reference, which means you can take advantage of the fact that you know that the other reference you have is not the same and that nothing else has that reference. So actually it's even almost even worse than C and C++, in that there's optimizations that the compiler and LLVM can do because Rust has these additional safety guarantees, such as the fact that there's not two mutable references to the same data at any one time. And I've forgotten what that's called, but yeah, that's the no alias pointers thing. So like pointers and references, you know that they're not pointing at the same data unless you've messed up your code and they are, in which case, yeah, all bets are off.
I'm just looking at the help for Rust Up doc. I'm just amazed. I didn't know about this earlier. You can bring up the standard library. You can bring up the cargo book, the Rust book, and loads of
Yeah, they will be very useful. Like when I'm traveling a train, often the internet connection is not too well.
Yeah, because it's local, isn't it? It's all. So I've had the Rustanomicon on my hard drive all this time, and I didn't know about it. I've been going to the browser like an idiot all this time and taking up my bandwidth.
Was the same for me.
Well, and Hugo's put us to rights. Yeah, so it's in the chat. Too bad undefined behavior is usually always bad and never anything good, like winning the lottery. So true, so true. It's so sad.